Okay, now I'm going to introduce the quotient rule similar to the way I introduced the product rule. Again, we know the derivative of x to the fifth is just 5x to the fourth. So what if I wrote it x to the fifth like this, x to the seventh over x squared? Again, the derivative would still be 5x to the fourth. Well, if you tried to thought that you could take the derivative of the top divided by the derivative of the bottom, then you would get 7x to the 6 over 2x squared, which is going to be 7x to the fourth over 2, which of course is not the right answer. So again, what went wrong is you tried to use a rule that didn't exist. For the derivative of a quotient, there's a rule here, right here. The derivative of the quotient of two functions, f of x over g of x. Now this one you have to be very careful with, because the numerator is a difference. So you've got to get this in the right order. So it would be g of x, which is the bottom function, times the derivative of f, which is the top function, minus f of x times the derivative of g. And then you have a denominator. You have to square the function that's on bottom. So it's g of x quantity squared. Now, the shorthand notation for this is that if you want to find the derivative of the function u over v, it's just v times u prime minus u times v prime all over v squared. Don't forget the denominator v squared. Now, let's see if this works on our problem. Now, I'm going to treat x to the seventh as u, and I'm going to treat x squared as v. So we know u is x to the seventh, so u prime would be 7x to the sixth. We know v is x squared, so v prime would be 2x. Now let's plug it into the formula. The numerator would be v times u prime, which would be x squared times 7x to the sixth, minus u times v prime, which would be x to the seventh times 2x, all over v squared. So that would be x squared squared. Well, the top, x squared times 7x to the sixth, is 7x to the eighth. And then x to the seventh times 2x is 2x to the eighth. So the top is 7x to the eighth minus 2x to the eighth. The bottom, x squared squared, is x to the fourth. So now the top is 7x to the eighth minus 2x to the eighth, which is 5x to the eighth. And then you divide that by x to the fourth. Well, x to the eighth divided by x to the fourth is just x to the fourth. So yay, we got it. We got the right derivative. So now let's do it on some. Again, you wouldn't want to use this rule on this particular function. But again, I'm just doing it to make a point. Now, let's start out with something fairly simple. Let's say you have a quotient where you have a binomial on top and a binomial on bottom. So the numerator is u, 1 minus 3x, and the denominator, v, is 2x minus 5. So the formula, remember, the numerator says v times u prime minus u times v prime. Well, so that means we take the v, which is 2x minus 5, from the denominator, and we're going to multiply it by the derivative of 1 minus 3x. And then we're going to minus u, which is 1 minus 3x, times the derivative of v, so the derivative of 2x minus 5. Now in the next step, I'll calculate the derivative. Oh, and don't forget, on the bottom, you have v squared. Obviously, you don't write this. This is just showing you that this is v squared. So 2x minus 5 quantity squared. Well, then you have 2x minus 5 times the derivative of this, which is minus 3. So you have 2x minus 5 times negative 3. Then minus 1 minus 3x from here, and then times the derivative of 2x minus 5, which is 2. And don't forget your denominator, 2x minus 5 quantity squared. Well, then just do a little bit of algebra. Distribute here, be careful with your signs. And you get minus 6x plus 15 minus the quantity 2 minus 6x. Well, it turns out that the minus 6x and the plus 6x, which is what you'll get here, will cancel, and you'll have 15 minus 2, which is just 13 for the numerator. So your answer is going to be 13 over 2x minus 5 quantity squared. Now, here's another one. Cube root of x over x squared plus 1. Well, cube root of x, notice I wrote it as x to the 1/3 so I can get its derivative. So here, the numerator is x to the 1/3. the denominator is x squared plus 1. So again, I'm going to do v times u prime minus u times v prime on top. So v is x squared plus 1, and then I multiply by the derivative of x to the 1/3, then minus u, which is x to the 1/3, times the derivative of v prime, so the derivative of x squared plus 1. Now, the next, and then on the bottom, I have the v squared, which would be the x squared plus 1 quantity squared. Now, calculate the derivative of x to the 1/3, and you get 1/3 x to the negative 2/3. And then calculate the derivative of x squared plus 1, and you get 2x all over this. Now, we could actually factor 1/3 x to the negative 2/3 from the numerator. Now, that's a little tricky, so you might want to do that on scratch paper. But basically, to factor it out of this term, there's really two terms here. There's this term, and then there's this term. Okay, so there's really just two terms. So if I factor 1/3 x to the negative 2/3 out of that term, that's the easy part. All I'm left with is the x squared plus 1. But if I factor it out of this part, well, here's what you got to understand. If you factor it out, you're really dividing this by 1/3. So if you divide this by 1/3, it's the same as multiplying by 3. So you've got to multiply by 3. And then also, what you're doing is, if you divide this by x to the negative 2/3, it's the same as multiplying this by x to the positive 2/3. So when you factor x to the negative 2/3 out, it's like multiplying this by x to the positive 2/3. Well, x to the 1/3 times x to the 2/3 is just x. So if you're wondering where that extra x came from, it's coming from x to the 2/3 times x to the 1/3. So anyway, when you get done with that, like I said, you might want to go to scratch paper to do that step. But anyway, you get x squared plus 1 minus 6x squared, which actually is just 1 minus 5x squared. And then I went ahead and moved x to the negative 2/3 to the denominator and changed its sign to positive. And then, of course, I had the x squared plus 1 quantity squared and 3 also in the denominator. Okay, here's one. Here's a trig function, sine x over x squared. Now, remember, the sine x is going to be the u, and the x squared is going to be the v. So, remember what we do. We take v. Now, here I'm just going to go ahead and get the derivatives in my head. So, I'm going to take v times the derivative of u. Well, what's the derivative of sine x? Cosine x. And then minus u, which is sine x, times the derivative of x squared, which is 2x. And then all over x squared squared, v squared. So now that's going to be x squared cosine x minus 2x sine x all over x to the 4th. Now there is one thing you can do here. You can factor an x out of the numerator and out of each term here, and then you can actually divide that x into the denominator and get x to the 3rd on the denominator. So there is a way to simplify that just a little bit further. So that gives you the derivative. So there's the final derivative of that function. Here's an example that uses multiple rules. So what I'll do is I'll apply the quotient rule first. I'll treat this is the u, and then the denominator will be v. So I'll take the denominator, v, and then look here, I'm going to say the derivative of u. So here's u. So I'm going to say v times the derivative of u, and then minus u, which is the numerator, and then times the derivative of v, all over v squared. These x's should actually be t's, since I'm using t for the variable. Okay, so now here, to get this derivative, I actually have to use the product rule. So let's do the product rule on this to get the derivative. So I take 5t minus 1, and then I multiply by the derivative of 3 minus 2t, which is negative 2. And then I take 3 minus 2t and multiply by the derivative of 5t minus 1, which is 5. And so I use the product rule there. And then over here, it's actually easier because I just bring this down, and then I have to get the derivative of 3t squared minus 2, which is just 6t. Now, from here on out, and then don't forget your denominator. From here on out, it's just algebra. So if you simplify what's in this bracket here and here, just do the algebra here, you should end up getting minus 20t plus 17. And then if you simplify this by multiplying it by 6t, you're going to get minus 60t cubed plus 102t squared minus 18t. And then you distribute your minus, and then they become plus. So, and then I left this for you to do. You can FOIL this together, FOIL these two together, and then combine like terms, and you should get, this is what I got when I did all that, minus 51t squared plus 58t minus 34 all over 3t squared minus 2 quantity squared. So again, you want to simplify that as far as you can. Now, here I want to find an equation to the tangent line. Notice I said equation to the tangent line of this function at x equals 2. Okay, now in order to find the equation of a tangent line, I need to know the y value. So I'm going to evaluate the function at 2 to get the y value. So you know how to do that. Just plug 2 in here to get the y value. So the ordered pair is the 0.25. But to get the slope, I need the derivative. Now remember, we got the derivative earlier for this function. So the derivative is 13 over 2x minus 5 quantity squared. So to find the slope at x equals 2, just plug 2 in to the derivative, and I get 13 over 4 minus 5 quantity squared, which is 13 over 1, or just 13. So the slope is 13. Now I use the point slope formula because I know the slope is 13. I know the point is the 0.25. So point slope formula, I'd have y minus 5 equals 13 times x minus 2, which is y minus 5 equals 13x minus 26. And then add 5 to both sides, and you get y equals 13x minus 21. And so that's the equation of the tangent line of the graph at x equals 2. Now what you might want to do is plot this function and then plot this point and graph this tangent line, and you'll actually see that this line is tangent to this function at that 0.25, and that'll let you see what's going on. Okay, I'm going to just let you pause the video and look at this if you want to. If you want to copy it down or take a picture, go ahead. But this is the proof of the product rule. And you'll notice that I proved the product rule using the definition of the derivative for the product rule. So again, I'm not going to go over this, but you can just read this, and if you want to see how to prove the product rule, then there it is. You could similarly prove the quotient rule, but it gets a little bit nasty since it's a quotient. So restart the video when you're done, and then you can look at the next examples. If you want to find the derivative of tangent x, now that we know the quotient rule, we can actually show you where it comes from. Tangent is sine x over cosine x. So if you use the quotient rule, you'll take cosine x times the derivative of sine x, which is cosine x, minus sine x times the derivative of cosine x, which is minus sine x, all over cosine x quantity squared. So you'll get cosine squared plus sine squared x over cosine squared x. Well, cosine squared plus sine squared is 1, so you get 1 over cosine squared x, which is just secant squared. So now you know where the derivative of tangent came from. And also you can do it for like another function, like if you want to find the derivative of cosecant, then you can write that as 1 over sine, and you can use the quotient rule there, and you can find out that with a little bit of manipulation, after you get that it's minus cosine x over sine squared x, you can actually write that as minus 1 over sine x times cosine x over sine x, and see that the derivative of cosecant is actually minus cosecant x cotangent x. And you can use similar techniques to show that the derivative of cotangent x is minus cosecant squared x, or that the derivative of secant x is actually secant x tangent x. And I left you with 2 more examples here, and you can pause the video. And the first one is a product rule, the second one is a quotient rule. And so if you need more examples, there's a couple more that you can look at. And that's the end of this section.